Welcome to This Explainer. Today, we're going to translate some pretty dense physics into the incredible story of how we discovered the invisible forces powering our modern world. In this chapter, we're exploring the very fabric of how energy travels through space. We're moving way beyond simple wires and magnets into something truly universal. Let's get right into it.
So let's start with a fundamental question that kind of changed physics forever. Now, you probably already know that an electric current produces a magnetic field, right? And thanks to Faraday's law, we know a changing magnetic field creates an electric field. But what about the reverse? Does an electric field changing with time actually generate a magnetic field? Well, to figure that out, we have to look at a totally brilliant deduction from the 19th century. Here is our roadmap for this explainer. First, the missing current mystery. Second, Maxwell's grand unification. Third, creating electromagnetic waves. Fourth, the anatomy of a wave. And finally, the electromagnetic spectrum.
Section 1. The missing current mystery. Okay, imagine a charging capacitor. If you measure the magnetic field outside the plates, boom, you find one. But if you measure it perfectly between the plates, where there's no physical wire, classical physics tells us the magnetic field should be absolutely zero. But here's the kicker. In reality, it isn't. Science literally cannot have contradictions like this. Ampere's law had a massive plot hole, and something was definitely missing. Section 2. Maxwell's grand unification.
Enter the Scottish physicist James Clerk Maxwell. He stepped up and realized what everyone else had missed. The changing electric flux between the plates was the exact missing link. He looked at that empty space and realized, hey, even though there are no physical charges flowing, there is an electric field between those plates, and it's getting stronger as the charge builds up over time.
So he introduced this entirely new concept called the displacement current. He mathematically proved that a time-varying electric field in a vacuum produces a magnetic field, exactly like flowing electrons do in a regular wire. So outside the capacitor, you've got your standard conduction current. But inside that gap, you have the displacement current. And they perfectly hand off to one another like a relay race.
This mind-blowing realization allowed Maxwell to finalize a set of 4 incredible equations. Along with the Lorentz force formula, these equations mathematically express literally all the basic laws of electromagnetism. The unified electricity and magnetism once and for all, proving that time-dependent electric and magnetic fields give rise to each other in this perfect, beautiful symmetry. Section 3. Creating electromagnetic waves.
So how are these fields actually generated in the real world? Well, stationary charges only produce static electric fields, and charges moving at a steady pace, they just produce steady magnetic fields. Neither of those create waves. But an accelerating charge, that is the trigger. It's kind of like a cosmic dance. An oscillating charge kicks off a self-sustaining ripple of regenerating fields. The oscillating electric field produces an oscillating magnetic field, which in turn acts as the source for the next electric field, radiating outward endlessly.
Now, while Maxwell provided the genius math behind all this, it was the German physicist Heinrich Hertz in 1887 who actually physically proved it. Hertz successfully produced and detected low-frequency electromagnetic waves right in his laboratory. And ironically enough, Hertz initially thought his discovery had absolutely zero practical use. Crazy, right? Yet his work sparked folks like Jagdish Chandra Bose in Calcutta, who produced even shorter wavelengths, and Guglielmo Marconi, who transmitted these waves over many kilometers, entirely kicking off the wireless communication revolution.
Section 4. Anatomy of a wave. Take a look at this. Notice how the electric field on the x-axis and the magnetic field on the y-axis are perfectly perpendicular to each other. And not only that, but they're also both perpendicular to the z-axis, which is the actual direction they are traveling. They are entirely self-sustaining. They require no physical medium to vibrate, meaning they can travel straight through the absolute vacuum of space. And right here is the absolute mic drop moment of classical physics. Seriously, Maxwell calculated the speed of these self-sustaining waves using his equations. He figured out that the speed depends strictly on the electric permittivity and magnetic permeability of free space. When you actually crunch those numbers, you get roughly 3 × 10⁸ meters per second. This was a massive revelation because it exactly matched the known speed of light, which led to the profound, game-changing conclusion that light itself is just an electromagnetic wave. Section 5. The electromagnetic spectrum. knowing that light is just a wave, we can see it's part of a much bigger family. From the radio waves carrying your phone calls, which are produced by accelerating charges in wires, to the microwaves generated by vacuum tubes heating your food, this spectrum literally dictates modern life. As we move up in frequency, we hit infrared waves radiating from hot bodies, which warm our planet. And right in the middle, visible light, born from atomic transitions. It's the only part of this massive spectrum we can actually see with our own eyes. There are no sharp borders here. It's just one continuous spectrum stretching from massive radio waves all the way down to tiny gamma rays. As we wrap up this explainer on this chapter of physics, take just a second to look around. You are currently sitting in a vast, invisible ocean of these self-sustaining waves. Wi-Fi networks, television broadcasts, the warmth radiating from your own body, and the light entering your eyes right this very second are all part of the exact same phenomenon predicted by James Clerk Maxwell. So, what other invisible fields might be shaping the reality right in front of you? Definitely something to think about the next time you heat up a meal or tune into a radio station.